Okay, so welcome to my supplemental recordings here about extra examples for section 7.3. Okay, so bear with me, please, while I confirm that my audio is set up correctly. Looks like it is. And then I need to share my screen. There we go. And then I've got my usual little bits of junk that I need to click on to get this going. Okay, all righty. So here we go. So there are 6 examples here that I'm going to go through about how to compute line integrals and surface integrals. And it's really just strategy. I'm not going to give you any mathematical tools that we haven't already talked about in class. This is just a little bit of kind of working experience and thought processes that I think are strategically effective. Okay, so roughly speaking, what I think, the process that I think students should go through is, for one thing, always look at the diagram. Always look at what you've been asked to compute. Identify where that is on which diagram. You got to make sure you're looking at the appropriate diagram. And then kind of, you'll build up experience, kind of visual to intellectual sort of, connections and cues that'll come from just, being at a particular place on the diagram. You do that enough times, you build up that experience. And then after having done that, compute what the diagram says to compute. Think about the boundary of whatever your domain is, and then there will be consequences that will come from those computations, certain conclusions you can draw about what's on the table, what you might possibly be able to use, and what is realistically you're not going to be able to use. Okay. And now, of course, also you want to always be somewhat heads up about coincidences, geometric good fortune. Sometimes you get lucky. Sometimes an integral is zero by symmetry. You want to always be on the lookout for these kinds of things as well. Okay. All right. So let's get started. Let's see an example here. We've got a vector field given. We've got a curve parameterized. We're asked to compute a line integral. Now, the sort of instinctive first thought that might occur to you here is, hey, I've got a parameterization. I can pull back through the parameterization. In other words, I can plug and chug. And I suppose you could do that. That's not going to be a good choice here. And you can see why. We've already talked about examples like this, because there's my formula for X, there's my formula for Y, and there's my formula for Z. And whoops, let me change the colors there. And so everywhere we've got a Z, right, we're really going to have e to the t squared plus t. And everywhere we've got an X, we're really going to have all that business over there. And everywhere we've got a Y, we're actually going to have all this other business. So that's going to turn the vector field into a nightmare. So very unlikely that that's what we'll end up doing. Okay, so let's take the advice. Let's go to the diagram. We're looking at a line integral. Great. Let's find a line integral on here. So here's 2 line integrals. Are these the ones I should be looking at? No, they're not. We're in the wrong diagram. Look at this. Yes, line integral, but this is a vector field that has 3 coordinates, right? The path has 3 coordinates. We are in R3. You cannot use the R2 diagram really in any way if the question is about R3. So you don't go into R2. We are in R3 for this question. So here's where we are. Here's the 2 line integrals that it might possibly be what I'm computing. Okay. Okay, and let's see, going back to the question. So yes, we have a vector field given. Oh, let's see what the diagram tells me to do with that vector field. The vector field that I have, the diagram tells me, yeah, that vector field, you should compute the curl of it. Okay. So I'm going to come back over here. I'm going to compute the curl of this vector field. Now, how to compute the curl, I have a little shortcut that, I mean, this is in my brain. This is how I do it. I remember that it's del cross, and that crosses are symbolic determinants. And so in my mind, and I don't write this down, but in my mind, I kind of see the del operator across here. And then in my mind, and I usually don't write this down. I'm doing this just for teaching purposes. I put my standard basis vectors up there. And then I proceed to take the determinant, and I take that symbolic determinant by going across the top row and for each such element, you know, so for example, for the top one, we do that and then that. And so I follow the usual determinant pattern, but really what it is it's reminding me which order do I take which partials of which components, right? So this little symbolic trick here is telling me take the y partial of that, which by the way is easily seen to be 1, minus the z partial of that, which again, easily seen to be 1. Okay, all right, so let's start writing this stuff down. So the curl of this vector field is, well, it was 1 minus 1. Okay, next we have 2x minus 2x. And then lastly, I guess we'll get rid of that. Lastly, I have 2y minus 2y. And so I get the 0 vector. Okay, so that's a good trick to keep in mind. Now, in practice, I emphasize I don't actually write all of that junk down. It takes up a lot of space. It's clunky, right? But that's just what I'm visualizing. So in my mind, what I actually do is I think that and that, and I just remember that this is saying y partial of that, and likewise. Okay, all right, so we took the curl, we got 0. Let's go back to our diagram. What does that tell us? We got 0, and that tells me that there is an anti-gradient. And so that tells me that I can use the fundamental theorem of line integrals if I want to. That's on the table. That's valid. Okay. Yeah, so that'd be one way to do it. Now, just to kind of flesh things out, let's go back to the diagram and consider our other options. Our other option that we're going to consider is based on looking at the curve that we have. And you know, you see right here the other conceivable theorem that might come in is Stokes's theorem, and we could, you know, ask, I wonder if I might be able to use Stokes's theorem here. Well, in order to be able to use Stokes's theorem, there's got to be an anti-boundary surface, right? And so now that's a arguably hard question, but whether there is or isn't such a thing relates very strongly, of course, to whether there isn't or is boundary points, right? So I need to look back at my parameterization here, and let's ask, does this curve start and end at the same 2 points, and thus being a closed curve, in which case there's an anti-boundary? Or might it be that this starts and ends at different points? And again, if you have a curve that starts and ends at different points, it's just not a boundary of anything. That's not a good fence. You can't keep sheep into the fence if the fence ends and starts at different points. That's just not how fences work, right? So conveniently, while the actual curve itself is going to be pretty hard to talk about, whether it starts and ends at the same point is a pretty easy thing to resolve. And I suppose different people have different preferences on how to most conveniently to see this. But I like to just note, okay, all right, well, when I plug in t equals 0, that third coordinate there clearly starts at e to the power of 0, namely 1. And where this curve ends, that third coordinate is going to be e to the power of 2, which is not 1. So these points clearly have different z coordinates. And if they have different z coordinates, they are different points. And so I don't even really have to write very much down. I can just kind of see from this one observation that no, this is not 0. So therefore, there's no anti-boundary surface. And that means that my question here, can I use Stokes' theorem? No, I cannot use Stokes' theorem. So we kind of have just the one option here. Well, okay, to be fair, we have two. There is an anti-gradient, which is why I can use the fundamental theorem of line integrals. But whenever there's an anti-gradient, that means another option is path independence. So if you wanted to, so you really, again, you have kind of two options here now. You could find the anti-gradient of that vector field and plug in the points, etc. Or your other option, you could find the starting and ending points, parameterize yourselves a straight line segment, almost certainly the most convenient choice, a straight line segment from the given start to the given end, because do keep in mind, we have to preserve the boundary, right? So, I mean, I can replace, sure, I can replace all of this nonsense with a different path that starts and ends at the same point. But I do have to start and end at that same point. So what do you think? You know, I mean, we have these two choices, and my own reaction is to think, you know, I don't think finding the anti-gradient is going to be that hard. I think I'd rather deal with the anti-gradient. Take a couple of anti-partials and then just plug in. I think that's going to be the winner. I think it's going to be the best way to do this problem. Okay. But again, if you want to do it this way, also fine. I do think that's going to be more work, though. So I encourage fundamental theorem of line integrals. Okay, so that's the analysis on that question. And I'm going to move on now to the next question. I'm going to leave no, you know, we just agreed on fundamental theorem of line integrals here. Make sure you can do that. Right, fill in those blanks. Make sure that you can actually crank out those details. We've already done examples of how to use fundamental theorem of line integrals, but make sure that you're strong with that. Okay. Now here's a not terribly different looking question. We're computing a line integral. We're clearly in 3 dimensions. Let's make sure we're in the right place. Okay, yeah, here we go. 3 dimensions. Let's clear the board. We're asked to compute a line integral. Okay, here we go. So we're looking at a line integral. That means that I should, in order to decide if there's an anti-gradient, I should take my vector field that I'm given and I should compute the curl of it and see what I get. And I guess I could do this. The same way. I'm about to compute the curl of this vector field, though super, super fast, because there's an easy observation to make. And that's that there's only x's in here, and there's only y's in there, and there's only z's in there. And in this process of computing the curl, the way we do it, you know, there's that, and there's that, and then there's, you know, the that and the that. Notice we're always taking what you might call off partials. I'm never going to be taking the x partial of this, only the y partial and the z partial. Well, there's no y's nor z's in here. And then likewise, in this term, we're going to be taking the x partial at some point. We'll be taking the z partial at some point. There's no x's nor z's in there. So right off the bat, I can just look at this because it's all x's, all y's, all z's. I know that the curl of this is 0. So it's a neat observation now, how often does this particular trick come up? Well, yeah, I don't know. Sometimes, but anyway, there it is. And how often you'll use this tool, I don't know. But this vector field does have curl equal to 0. Okay, so taking stock, yes, I did get 0. That means that there is an anti-gradient. And so fundamental theorem of line integrals is on the table, which is nice, I guess. Here's the thing, though. If I were to use the fundamental theorem of line integrals here, I would seem that my first step would be to take the anti-gradient, in which case I would need to compute the x anti-partial of x squared e to the x. Not that I can't do that, but that's annoying. That's integrating by parts twice. And then I'd have to take the y anti-partial of y sine y. And again, you know, worse things have happened. I guess I could do that. But then even worse, I'm going to have to take the z anti-partial of e to the z squared. And whoops, missed. And y'all may have seen this particular integral before. You can't analytically what they call closed form antiderivative for this integral. It can't be done. So without doing sequences in series or something like that, there is no antiderivative that you can write down. There is an antiderivative. I emphasize, it's just that you can't write it down in usual terms. Okay. So with fundamental theorem of line integrals is not looking good. All right, so let's consider our other option going back over to here. So I'm going to kind of erase all of this and say, I'm going to put a, maybe over there. So let's ask the question then, can I use Stokes's theorem? How do I decide if I can use Stokes's theorem? Well, my curve that I'm given, it has to be a boundary of some surface. It needs an anti-boundary surface. Again, how do I decide on that? I look at the boundary points and I ask, are those boundary points the same? In which case they kind of cancel it. I mean, if they start and end at the same point, then they kind of neither starts nor ends there, right? Or not. So we look at what we've got here. And again, I'm going to plug in t equals 0. And let's write this down. When you plug in t equals 0, you get x of 0 is, well, okay, 0. Then I have e to the power of 0, which is 1. And then e to the power of 0, which is 1. Okay. Now let's look at our stop point. Let's plug in t equals 1. We get x of 1 is, okay, well, let's see here, 1 times sine of pi, which is 0. Let's see, then e to the power of, let's see, sine of pi is 0. So e to the 0, which is 1. And then the e to the 0, which is 1. So this curve itself, the curve is some sort of a nightmare, right? But it starts, well, it's going along, where it started, right? And where it ends up when it's all said and done, same point. And so really what you've got is a closed curve. And so there is an anti-boundary. There is going to be, some sort of a surface in there whose boundary is this curve. Okay. All righty. Right. So let's see here. So yeah, so this is 0. And so yes, there is an anti-boundary surface. And so yes, you can use Stokes's theorem. The problem here, the problem here is that it's real hard to write down what this surface is, right? I mean, in order to understand the surface itself, if I wanted to understand this surface, I really would need to have a better understanding of the curve, and the curve is all kinds of weird. So, neither one of these approaches is looking all that great. We're about to have a super happy ending here, but neither one of the approaches is looking good. This, Stokes's approach is not looking good because the surface is going to be brutal to find. The fundamental theorem of line integrals approach is looking not good because the anti-gradient is going to be hard to find. So let's back to the diagram. Yes, I can use this theorem, but I don't know how to find that anti-gradient function. Yes, I can use this theorem, but I don't know how to find that anti-boundary surface. Okay, so here's the good news. Here's where everything comes together on this question, and this is not a particularly rare occurrence. And when this occurrence happens, this is a really nice sort of bit of good fortune to know about. Here's what happens. The point turns into, effectively, not that there is an anti-boundary surface, but that the boundary of the original curve is nothing. It's 2 points that are the same. It's the same A and B. And so when I am looking at the fundamental theorem of line integrals here, computing f of b minus f of a, sure, I don't know how to do f. F is hard. That little f, the anti-gradient, I don't even know how to find that, but I'm putting the same point into it twice and subtracting. So this is really kind of f of a minus f of a. It's sort of obviously 0. So happens to be 0. Which is, it's nice that this works out. And here's another equally beautiful way that you can approach this problem, another equally beautiful observation. The fact that there is an anti-gradient, again, turns out not to be the point for this question. The point here is that this curl of the original gradient is 0. And so while when I'm looking at Stokes's theorem, looking at this flux down here, the surface, I don't know. The surface is, I don't know how to find that surface. That's going to be hard. Okay, well, yeah, but fine. But what am I taking a flux of through that surface? I'm taking a flux of 0, right? So that approach also works really, really well. So in fact, it turns out, and I think this is a pretty easy pitch, that whenever both of your theorem options on either side of the thing that you're trying to compute, whenever they both apply, namely when there, is, let me color code better than this, when, you can use this theorem because there is an anti-gradient function, even if you can't find it. And also that there is an anti-boundary surface, even if you can't find it. The mere fact that these are both there tells you that, yeah, but that's going to be evaluated over 0. And this is going to be, you're basically plugging in the same 2 points into it. And so you're going to get 0. The answer to the question is going to be 0 every time. As long as both theorems apply, you are going to get 0 as your answer. So neat trick. Now, I emphasize, you do have to give me the mathematical argument. I am not proving this theorem. This is a plausibility argument that I'm giving you. This is notice the good news, right? You do have to give me an argument. So we go back to here, and now let's write down what our argument would be. And here we go. So having observed all that we did above, I'm going to show you the fundamental theorem of line integrals argument first. Fundamental theorem of line integrals would say that curl is 0. And that implies that we have the anti-gradient and so our integral is f of b minus f of a, which is f of a minus f of a, which is 0. All right, so that's really easy to write down. This hits all the big ideas. Totally fine, full credit right here. Bam. Okay. All right, now let me show you, if you, on the other hand, if you wanted to do the Stokes argument, and I just need to, oops, I just need to get this out of my own way here. The Stokes argument would go like this. Okay. So let's see, x of 0 equals x of 1, which implies that this is a closed curve, which implies that my curve, did I name my curve? I did not name it. Well, anyway, I'm going to name it C, is the boundary of some surface S. Then my line integral is flux through S of the curl dot ds, which is the flux of the 0 vector dot ds, which is 0. Full credit, no problem. So take your pick, either approach that you like. It's all good. Now, I emphasize, just to be completely clear, I mean, again, you do have to explain how you know that these things exist. It is a huge part of this problem to know that there is an anti-gradient. When there's no anti-gradient, this is complete nonsense, and nothing over here is true if, in fact, there is no anti-gradient at all, right? So that is a dangerous bit, and you got to make sure not to step on that landmine and just kind of gloss over. You got to give me the argument. And again, it's not about whether you have the right answer; it's about whether your argument makes sense, right? So don't oh, in my mind, oh, can't get this to erase. In my mind, I knew that there was an anti-gradient. I just didn't write it down. No, you got to write it down. You get points for what you write down on the page, right? So make sure to document your reasoning. Just to be clear, this right here is not worth much, really. Probably some sympathy points maybe, but this is not a complete argument, and this misses a huge part of the problem. This might be, I'm not going to speculate how many points, because I don't want to paint myself into a corner. It depends on the details of the question, but anyway, this is not good right here. Okay, and likewise, if you don't include this, right, and you give me just this right here, that's not worth much either, right? If you don't explain how you know that there is that anti-boundary surface. If you just assert that there's some surface out there, right? Nope. No, absolutely doesn't work. Lots and lots of curves. Most curves, perhaps, right, are not closed. And at least half of the idea of the argument is that curve exists. So you got to document, and again, don't make that mistake. So again, as written here, not good credit. This, full credit, no question. Good job. That's a big difference. Okay, so be very careful with that. Okay, so I'm going to stop this recording here. We've discussed these first two examples, and I'm going to go on with the next recording and talk about examples 3 and 4. Okay.